So here's where we left off at the half equivalence point. Let's just move on to the full equivalence point. So at this point we will have added an equal amount of hydroxide titrant to our weak acid. These two will both go to 0, and all of our HA will be converted into its conjugate base. So visually, that's shown here. But then, this conjugate base is going to react with water, forming hydroxide and reproducing a small amount of HA. And so there's our small amount of HA, and the production of hydroxide drives the pH to higher values. And we can determine the pH by first determining the pOH, which we know how to do for a weak base solution. So let's do that now. And I'll warn you that this is the most involved calculation in our titration curve, unlike in the strong acid, strong base, where we just said pH equals 7. Now there's the long way, and there's the even longer way to do this. The even longer way involves showing every single mathematical step, and so that I'm just putting on this slide because we're going to learn the quicker way. But what would happen is we would write out the neutralization reaction. We would see that indeed our reactants are equal in amounts, so they both go to 0. In turn, the conjugate base goes up by that same amount that these went down by, and we would have 5.00 millimoles, which we would then divide by the new volume of solution and get a concentration for this conjugate base of 0.0333 and then little 3 molarity. And with that concentration and the Kb value, which we can get from the Ka value, we can figure out pOH and pH. But let's just see a faster way to get to this point. So point C, equivalence volume, 50.0 milliliters. We'll make the quick note that we switch to the conjugate base point of view. Switch to conjugate base point of view, or POV, because that's all we have at the equivalence point. And the concentration of this conjugate base is different than the concentration of the acid that created it. And so the first thing we have to do is figure out that concentration of A-. Notice I'm leaving some space between here, and that's because I'm going to be writing some notes above the math that I'm going to write over here. And so we already saw the long way to figure this out. That was what was on the previous slide. Here's the faster way. We will set this equal to the initial concentration of our weak acid, HA, times the initial volume of said weak acid. And we will divide by the volume of the solution post-titration. And so how does this math work? Well, when you multiply the initial concentration of that weak acid by its volume, what you're going to get is the initial moles of the weak acid, moles of HA initial. And we already saw that at the equivalence point, you have just 100% converted every one of those moles into a mole of its conjugate base. So the moles of HA that you start with are the moles of A- that you have at the equivalence point. But the volume that those moles are swimming in is larger than it was initially because we've added these 50 milliliters of base. And so from this we'll get our concentration of conjugate base at equivalence point. And that's just plugging numbers in. 0.0500 molar was our initial concentration of acid. Its initial volume was 100.0 milliliters. And then we divide that by the new volume of solution, which is just 150.0 milliliters. And we get 0.0333, and then we'll keep one more digit for now. And this is in agreement with what we saw in the long way on the previous slide. So now what do we do with that value? Well, we know that what the A- is going to do in water is take a proton, reform HA, and leave behind hydroxide. And we'll take that concentration 0.0333 little 3. We will subtract x from it, and we know that these two species here will go up by that same amount. And then we just need to plug that into a k expression. But, of course, that k expression needs to be based on the kb, which we know how to find from the ka. So let's do that. I'm going to erase this to give me some room. So our kb of A minus is just going to be equal to the kw divided by the Ka of our weak acid, which we already found back when we did point A. It was 2.5 little 1 times 10 to the minus 6. And then up top we'll just put the Kw, 1.0 times 10 to the minus 14. And so that would give us our Kb. And on the right side of our K expression is what we've seen numerous times at this point, x squared over concentration 0.0333 little 3 minus x. And then we solve the way we've been doing. Solve for x, use the small x, do the check, then take the negative log of what you get, and you should get not the pH but the pOH, and that is equal to 4.93, not ready to round yet, little 9. And if you're having trouble figuring out the sig figs right now, what we have is a 2 sig fig number over here, divided by another 2 sig fig number. We're just keeping one extra digit for now. And then on this side we have a 3 sig fig number with an extra digit. But all that matters is that we have 2 sig figs over here, so when we do all of our multiplication and division, our x value should have 2 sig figs. And when we take the log, we know that only numbers to the right of the decimal point count as sig figs. So these are the 2, but we're keeping one more digit because we are not ready to round. We have one more thing to do. And that thing is to subtract the pOH from 14. And then we will get pH is equal to 9.06. And now I'm rounding to 2 sig figs. Notice that this pH is basic, not neutral. Basic, not neutral. We weren't able to just say pH equals 7 at the equivalence point like we did with a strong acid being titrated. And that makes sense, because when we did a strong acid, strong base titration, water was effectively the only product. But in this case, we're producing an actual weak base. Let's quickly delve more into that, and then we'll draw the point in on the titration curve. Take, for example, a strong acid like HCl meeting a strong base like NaOH. We know that in aqueous solution, these have 100% dissociated into ineffectively weak and unreactive conjugate acids and bases, and protons and hydroxide ions, and these are what really react in the titration, producing water. When you have equal amounts of those at the equivalence point, they both annihilate each other, and we're left with nothing but H2O and these unreactive ions. And since these aren't actually doing anything, we effectively just have water and thus a neutral pH. But when a weak acid like acetic acid reacts with a strong base, this is what's really going on. The NaOH still 100% becomes an ineffective and unreactive acid and hydroxide ions. But that acetic acid doesn't dissociate much. We will get a small portion of protons from it that in theory can react with the hydroxide from the strong base, but there's so much more Hc2, H3O2 that just remains intact that the hydroxide's much more likely to find one of these in solution and react to form conjugate base and H2O. And so when we have equal amounts of the weak acid and hydroxide, well, we're not just left with water, we also have a conjugate base, and that is what's going to lead to a basic pH value, which is why we got 9.06 rather than 7. So now let's fill out that titration curve. So at 50 milliliters, we have a pH of a little above 9. And the way that we're going to connect point C to point B, so we're going to start at point B and continue our shallow rise because we're in this buffer region. And then once we're out of it, we're going to do a sharp climb to equivalence point like what we saw before. So sharp rise around VE. From here, life actually gets a lot easier. In fact, there's nothing new to learn, and let's see what I mean by that. And so we left off at the equivalence point where all of our acid has been converted into its conjugate base. A small portion of that conjugate base will reform HA and also generate hydroxide, driving the pH higher. But if I were to keep on adding hydroxide from this strong base titrant, most of that is just going to go right into solution. We're in what we call an excess OH- region, and we saw this with the strong acid, strong base titration after the equivalence point. In principle, some of it might find this small fraction of weak acid that's swimming around in solution, but most of it's just going to go in there. And we can calculate the concentration of that unreacted excess hydroxide ion that we just put in solution using the same math as we did when we got to point D of the strong acid, strong base titration. So this you already have in your notes from before. You can write it again. I'm not going to bother handwriting it because, again, we already did it back when we did this titration. I will point out that in principle we have some hydroxide being formed from the conjugate base that's swimming in solution, but at this point it's negligible compared to the hydroxide ions that we're just dumping in from that strong base titrant. So let's make some final notes. Point D, 3/2 of the equivalence point, 75.0 milliliters. And that's just so that I continue with the trend of going up by 25 mils each time. At this point, we are in the OH- excess region. And we'll just say it's the same math as point D for the strong acid, strong base. Same math as point D for the strong acid, strong base. And we can also say that there is a slide that shows it off, so see slide. And we'll also stress that the hydroxide contribution from A- is negligible to the hydroxide from the strong base. The hydroxide contribution from A- is negligible to the hydroxide from the strong base. To the hydroxide from strong base. And let's just end the video by adding that point to our curve. The pH was 12.155 using that math. And then we'll connect that to point C by continuing the sharp rise at C, then having it level off some towards point D. And so there we have all of the important points and regions of our curve. The next step is to see how we would use that data analytically. And I kind of already hinted at some of that when I discussed point B, but we'll just get into that later.